Hi there! We looked today in class at some more optimization problems, and so I've selected two examples to demonstrate some of the problems that we considered today. There are, of course, other videos on my website. There's the filled out notes that we worked on in class by period. And then, as always, I'm available to answer questions or provide extra assistance as needed. Just feel free to email me or swing by my classroom or whatever you would prefer. Okay, so the first one we're going to look at here is example 13. Which says, a manufacturer wants to design a box having a base where the length is twice the width. The surface area must be exactly 300 inches squared. What dimensions will produce a box of maximum volume? Okay. So step one, let's go ahead and start with drawing our box here. Okay. And labeling it. Okay. Now you want to make sure as you're labeling your box, don't just go along and label each side a different variable. Make sure to consider what information they've given you. In this particular problem, they've told us that the base, or that along the base, the length is twice the width. Right? And so whatever you label your box, you do want to make sure you've taken into consideration that relationship, that on that base, the length is twice the width. Okay, so I'm going to go ahead and call this side x, which means this side would need to be 2x because they're along the base of my shape. Length is twice the width. Okay? And then I can call my height over here, let's go ahead and call it y. Because that one we aren't told any relationship regarding. Okay? So now that we've gotten that taken care of, we're going to go ahead and proceed to step 2, which is to write a primary equation. Now, a primary equation is what we are trying to maximize or minimize. In this particular case, we are asked about maximum volume. And so volume is going to be my primary equation. Okay? For this one, volume of a rectangular prism is length times width times height. Length times width times height. Okay? Now I don't want to put though L times W times H because that doesn't make sense for my picture. So I'm going to go ahead and use my volume equation, but I'm going to substitute in my variables. And so I'm going to go ahead and call this x times 2x times y, which of course I can clean up a little bit and call this instead 2x squared y. Okay, there's my primary. My secondary equation then is something that's given. It might be a relationship, it might be a given quantity, but something else that's given. In this particular case, we're told that the surface area must be exactly 300 inches squared, and so that's going to be my secondary equation. Okay, and surface area of a rectangular prism is 2 of every pair, 2 length width, 2 length height, 2 width height. But again, I don't want to just put in that equation because that doesn't make sense for my rectangle, and so I'm going to, or my rectangular prism, so I'm going to go ahead and use my variables within this equation. So we have 2, my length times my width, so x and 2x. Then I have 2, my length times my height, so 2x and y, and then 2 of my width and my height, so my x and my y. Again, 2 of every pair. We have x and 2x here, where my pin's pointing. I'm pointing with my fingers at the pair, and then my pin's pointing at where I wrote it, so we have x and 2x. We have 2x and y, and we have x and y. Right, 2 of every pair. Okay, again, I would recommend cleaning this up a little bit. So we're going to go ahead and make this first term 4x squared, the second term is 4xy, and the third term is 2xy. And then I notice that I have like terms here that I can combine, so I'm going to go ahead and take a moment and do that as well. This is 6xy. Okay, so now that we've got that, we've got our primary, our secondary, we're on to our next step, which is to substitute something into my primary equation to get this in terms of one variable. Okay, I'm going to go ahead and choose to solve for y in this case because I noticed looking at it that y is all by itself over here. There's only one y as opposed to two x's, right? And so y seems simpler. Okay, so I'm going to go ahead and subtract the 4x squared over. And then I'm going to divide everything by that 6x. Okay. So dividing 6x on this side, we have just y left over. 300 divided by 6x is 50 over x. And 4x squared divided by 6x is 2/3 x. Okay, so now I can take this and I can plug it into y over here. At this point, you're now on to the next step, which is to take the derivative and set it equal to 0. You could do product rule here, but I'm going to go ahead and choose to distribute n so that I can just do power rule. So 2x squared, 50 over x, gives me 100x. And 2x squared, 2/3 x, gives me 4/3 x cubed. And that's where I'm then going to take the derivative. And set it equal to 0. Okay, derivative of 100x is 100. Derivative of 4/3 x cubed is 4x squared. And now I can solve for x. Go ahead and add that 4x squared over, divide the 4 over, and I get x equals 5. And my units in this case are inches. Okay, last step, you do want to make sure that you've always taken the time to actually answer the question. And so when I look at this, I see that I'm asked for the dimensions that will produce a box of maximum volume. So I have the x, which means I want to know what my other dimension or dimensions would be. Okay, so I can solve for y in this case by plugging in to my y equals. Okay. So we have y equals, and it's 50 over x. Well, x in this case is 5, so we have 50 divided by 5, which is 10, minus 2/3 times x, so 2/3 times 5, which is 10/3. And 10 minus 10/3 is 20/3, and again, inches for my units. The third and final dimension would be this 2x, right? Because x was 5 inches, y was 20/3 inches. The final dimension is this 2x. Well, 2x is 10. And so we've got 5 inches by 10 inches by 20/3. 20/3, I should say, inches. And those are my dimensions. Okay. Go ahead and do one more here. Example 10, which says a window is being built. The bottom is a rectangle, and the top is a semicircle. Okay. If there is 12 meters of framing material, what would be the dimensions of the window to let in the most light? Okay, I'm going to go ahead and label this rectangle as xy. And then with a semicircle, when I think about a semicircle's equations, those are always with r's in them, right? When you think about circle equations. So I want to go ahead and label the r of my semicircle here. And in this case, that r is half of this side. It's half of x. And so that's my r. Okay, so here's my picture. Primary equation. Okay, primary equation, what am I looking to maximize or minimize? In this case, they're asking me what would be the dimensions to let in the most light. Okay, that's not specifically referring to a particular equation, but you can figure out what that is. Picture a window, picture letting in the most light. What are we talking about when that happens? We're talking about area, right? The area of the window would let in the most light. Okay, and so area is my primary equation. Okay, for this shape over here, the rectangle's area is pretty easy, right? X, Y. The semicircle's equation could potentially prove a little bit more challenging. Remember, it's a semicircle, it's half a circle. And so I'm going to go ahead and do my circle work just kind of up here, kind of off to the side a little bit here. So a circle area I know is pi r squared, right? Which means a semicircle would be 1/2 of that. Only I don't have an r, right? So I want to go ahead and put in what I call my r, which is 1/2 x quantity squared. Okay, so that's what 1/2 x is. 1/2 x and r are the same thing. And you could put that in here, or you could clean this up a little bit first if you wanted to. So I went ahead and squared the 1/2 and the x to make 1/4 x squared, and I did 1/2 times 1/4 to get 1/8. So that's actually what I'm going to choose to put in. Again, you do not have to. You're going to get the same answer no matter what, even if you left it as 1/2 and 1/4, because those are just coefficients. They'd result in the same answer. Okay. My secondary equation then is what they have provided for me. In this particular problem, they have provided for me that I have 12 meters of framing material. Okay, so that's what I need to be figuring out, is what makes up that 12. Well, for that, I'm going to pretend I'm the framer, and I'm just going to work around my shape. This side here is a y, and an x, and another y. So I have 2 y's and an x. And then my semicircle, right? Okay, so again, I'm going to do my work up here. A circle's circumference would be 2 pi r. This is a semicircle, so I'm going to do 1/2 of that. Okay, but I don't have an r, I have 1/2 x, and so I'm going to take this 1/2 x and put it into r there. Okay, so we have pi and 1/2 x. And there is my secondary equation. Okay, next step, we're going to go ahead and isolate a variable. I'm going to choose to isolate y. So I'm going to subtract the x over and subtract that 1/2 pi x. Okay. And then I need to divide that 2. So 12 divided by 2 is 6. X divided by 2 is 1/2 x. 1/2 pi x divided by 2 is 1/4 pi x. And 2y divided by 2 is y. And so that then is what I'm going to substitute into that y spot over there. Go ahead and draw a little line down here, kind of separating our work, making sure we don't get that mixed up. Okay, at that point you're going to go ahead and take the derivative and set it equal to 0. So you can take the derivative as is, or I'm going to choose to go ahead and distribute this in so that I've just got power rule to worry about. Okay. So my derivative in this particular case, that I'm going to set equal to 0, is going to be derivative of 6x, 6. Derivative of 1/2 x squared is x. Derivative of 1/4 pi x squared is 1/2 pi x. And derivative of 1/8 pi x squared is 1/4 pi x. Okay, at which point we're going to solve for x. Okay, so I'm going to choose to go ahead and subtract this 6 over to the other side. Just going to separate all the terms that have no x from all the terms that do have an x, which then allows me, since all of these terms have x's, to factor an x out. And now that I have two things, x and this quantity being multiplied together, I can separate them by doing the inverse. I can divide this quantity to the other side, which will give me x. Okay. And if you noticed, I left my denominator in parentheses in this particular case because I'm going to go ahead and plug this into my calculator. That way, so we want the parentheses in there so that our calculator makes sure to put all of these three terms in the denominator. If you don't put parentheses around them, it's going to do order of operations. It'll divide the -1, but it won't put the -1/2 pi plus 1/4 pi in the denominator with it. It'll instead add these two terms off to the side of the fraction. Right? So you do want to make sure parentheses are put around them. Okay, so here we go. We've got our -6 divided by parenthesis -1 minus 1/2 pi plus 1/4 pi, which gives us about 3.36, and then you can either call it 0 or round up and call it 1. And my units in this case are meters. And my other dimension would be my y equals, okay, well my y equals this 6 minus 1/2 x minus 1/4 pi x. Okay, so you have a choice you need to make here. Okay, either you can plug in this whole fraction into the x's spot, okay, or you can put in the decimal, but if you're going to put in the decimal, you need to make sure you aren't just putting in this 3.361. You need to store it, or for me, because mine's right here, right above it, I'm just going to hit up and hit enter and select it. Right, but you want to make sure you use the whole decimal as you continue here. Okay, so my y is 6 minus, right, 1/2 of my x, okay, and my x in this particular case is that decimal, so I'm going to go ahead and hit up so that my decimal is selected, and I'm going to hit enter, which will allow, whoops, let me put in a times there, okay, which will allow, when I hit enter, my calculator to auto input that decimal. Okay, then I have minus 1/4 pi, right, minus 1/4 pi. And then again x, so go ahead and hit up, select enter, so you've selected it, you've inputted it, and that gives me the 1.680. And then again meters. And there you go.